Oh, is it already time? Hey, hey. Welcome back to Southern Sweden for another lecture in the course Design of Embedded and Intelligent Systems. My name is Martin. It's quite cold here today in Sweden, so I hope you have some warm coffee or something. Let's get started. Today we're talking about recognition. So our goal is to think a little bit about how we know what we know and what this means for designing embedded and intelligent systems. So why do we care about this? Oh, wait, I'm sorry. I have to take this. Hi. Oh, is it you again, Elon Musk? Oh, yeah, billions of dollars saving lots of lives. Yes, I'm sure they also understand, they also recognize that recognition is very important. Sorry, gotta go. So what is recognition? Artificial intelligence is a little bit of an elusive and interesting concept because we can imagine that it's like a search where maybe you're looking for the bottom of some function, the minimum. You can look at it sort of as a labeling problem. If you get some new thing, what number can you assign to that new thing? It's got a lot of math in it often, so you're multiplying, adding matrices and stuff like that. And it really seems almost magical, some of the stuff that you can do with AI. You can tell things from very small cues that maybe humans can't even detect. In some areas, AIs are performing as well as humans, in other areas even better than humans. DARPA has described AI in terms of three waves. The first one is handcrafted AI by experts, so they encode their knowledge directly into some rules. The second one is statistical learning, where you have some type of algorithm that can learn a good approach to solving problems without having all of the information specified. This is what we're going to focus on today. And the third is context-aware stuff, so explainable AI, trustworthy AI. So artificial intelligence is not human. Again, robots can do stuff like sensing infrared, ultraviolet and stuff that humans can't do, but we can take a lot of inspiration from humans. So what is human intelligence like? Well, human intelligence is self-aware, it's adaptive, and it's multi-level. So for adaptivity, there's some concepts that you should know about if you don't know already, like data drift, that in real life situations, often situations change, the context changes, and the type of data that you get into your system changes. So your system has to deal with that. That's also described by plasticity stability. The system has to be flexible enough to deal with new stuff, but still stable and able to function well. So multi-level knowledge, two taxonomies describing human knowledge are the Solo taxonomy and knowledge pyramid. The Solo taxonomy is used in teaching, and it says that there's sort of levels of knowledge, like multi-structural knowledge. You can list information. Relationally, you can also relate the things that you've listed together. And hypothesis, you can come up with new ideas. The knowledge pyramid also has this idea of low-level data that can be processed, and then you can do more complicated recognition tasks with information or knowledge, and finally wisdom. But this doesn't explain really how humans know the stuff that they know. So we start with this question: what is our reality? What is our knowledge? And one answer to that is constructivist epistemology, based on statistical inference, that we construct our knowledge from statistically. So we observe our world, and we infer stuff about our world, and then we act and we observe again and continue that loop. We also communicate with other people, and we develop beliefs, which we also use in our inference. So in this course, we look at two types of this key inference part. We look at recognition, which is like what robots can use to classify and do regression. And we also look at some inference for evaluation, basically scientific method type of stuff. And this will be done in a later lecture. So how do we do recognition? Well, in machine learning, a typical approach is one, to prepare some data, we acquire it, we observe it, and if you're doing some type of supervised or semi-supervised learning, you'll label some data and you'll have some idea of what classes you're going to use. Two, you select a recognition approach. That means some technique like SVMs. You'll have some parameters, maybe that might be C and gamma for SVMs, and you might also have some features. Three, training and evaluating. So that's testing and then refining your system as well. So for the second step, I should add that, again, we have different types of recognition. We can do classification, where you say, is some new thing class A or class B? Is this a robot? Is it a human? Or we have regression, where we assign a number to this thing. That could be like, how fast is the robot going? It's going at 1 meter per second. Linear or non-linear. So you remember that for simple problems, we can use some type of linear system, which might give an optimal solution. For more difficult problems, often when you have humans in the loop, your problems can be quite complicated, and then you can use maybe a non-linear system. If you're using features, you should make sure that these features are good for telling the difference between your classes, or giving you a good score for regression. So one way to do that is to look at your data. The third step, some things that are useful for training and evaluating, cross-validation and confusion matrices, and we'll talk about this later. Oh no, we've got an emergency. We have to answer some questions about features. So we've got three scenarios here. If you want, you can consider what kind of features you could use in these scenarios and stop your video for a little while. I'll assume that you've done that now, and I'll go on. Okay, case A. We've got something on the left that's a bit dark, something on the right that's a bit light. So what can we use? Well, we can use the mean intensity of the image or the median intensity of the image. So when would you use the median and not the mean? When you maybe have lots of outliers that you don't want to take into account. Having said that, the mean can also be useful. B, you've got something on the left which is very, very uniform. You've got something on the right which is very different depending on which half of the image you're looking at. What could you use? Well, for example, standard deviation or variance would give you a big difference for these. C, we have another difficult case with some camouflaged animals. So on the left, this is a lizard. The second one is a chameleon. The third one is a stick insect. And the fourth image on the very right is an octopus. What could you do to detect these? Well, I don't think there is such a good answer. These animals are very good at hiding themselves. You could try to use a thermal camera to see if you can see their heat signature, if that's different from the surroundings. You can watch over time to see if they sometimes move in a different way than their environment, like leaves or whatever. Maybe they'll move from tree to tree, scurry around. But I think the lesson here is that in general, finding good features can be quite hard sometimes for real life problems. That's often the case. Other stuff that people do with features often is they often scale or normalize their features. And you can do this typically in two different ways. You can have some type of range like between 0 and 1, or you can do it statistically. So if you want to do 0 and 1, you should just check in when you're processing test data that you also use the same max and min. So you can just floor and ceiling your data and then use this function here to calculate the value between 0 and 1. Shuffling and smoothing is also very common. But when you're thinking about this type of pre-processing stuff, we should really try to keep things simple as researchers. We don't want to do stuff for no reason that's maybe even not helping to solve the problem. Maybe it's even giving us worse accuracy. So then it's nice to do some type of ablative study and check each thing that you're doing. Does it really help you? Parameters, we often have to make some type of choice in the parameters, which can affect the variance and bias. I think you've heard these terms before, but if you have high variance, then your system might be overfitting. You might have some very complicated decision boundary. If you have high bias, your system might be underfitting. So you have just maybe this line when your data is definitely not easily separated by a line. Another thing that's useful to know about is distances and norms. So why do we want to know this? Well, we want to have some type of way to assign numbers to a vector and some way to understand the differences and distances between different vectors when we're calculating features and also for our cost functions. And the two main distances that people use are L2, Euclidean distance, and that's what everybody uses going to school as a child, and L1, the Manhattan distance. But we also have other distances. So I think maybe you know L2 Euclidean, it's the shortest distance. So if you look here at this example at the bottom, this vector over here, V, the norm would be the square root of 5 there. And for the Manhattan distance, you just count these line segments that you have to follow to get to your destination. So here we have to go up 1 and then 2 to the right, or we could go 2 to the right and up 1, and that would be 3. We also have two other distances that I mentioned for some other distances that I mentioned for people who want to know a bit more. So L0 is the total number of non-zero elements. Hamming is the number of bits to change. Mahalanobis is also, you see this quite commonly, and it's basically just using an ellipse, not a circle. It's weighted. L infinity, Chebyshev, or chessboard distance. You can just imagine that you're the king in a chessboard that can move in any direction, and one of those, then it's the number of moves that would take you to get to your destination, looking at it like that. So we've got another little quiz here. What would be the distance here? For A, what would be L1, L2? For B, what is the Hamming distance? I assume that you've paused the video if you wanted to. Well, the answer for A, if we look at it, L1, you have to go up 1 and to the right 1. So that would be 2. And for L2, this is Pythagorean theorem stuff. So it would be the square root of 1 plus 1, or the square root of 2. You can see that's shorter than L1 there. Hamming, well, you've got 2 bits that are different, so the answer is 2. And we go on just a little bit more on the same topic. Why would you use L1? Why would you use L2? L1 is more sparse. It's better for feature selection because L2 penalizes large coefficients. L1 is more robust to outliers because the cost isn't squared. L2 is simpler, so you have one solution rather than many, and it's easier and faster to calculate. It's also, the claim is that it's more stable sometimes. If you have a small nudge, your decision boundary won't be so easy for that to be changed very much as a count of that small nudge. Pattern recognition techniques. So there is very, very many techniques that you can use to do recognition. The very simplest thing is heuristics and thresholds. So you can say, you know, if something that you're looking at is greater than 100, then it's class A, otherwise it's class B. Decision tree sort of takes this to the next level. You can have multiple heuristics arranged somehow. You can have ensembles like boosting or random forests. You can have mixture models like a Gaussian mixture model. Today we'll talk a little bit about maybe 4 types of recognition techniques: K-nearest neighbor, KNN, support vector machines, SVMs, K-means, and neural networks like deep learning stuff. So first, the first thing we're looking at, K-nearest neighbor. Why is this useful to know about? Because it's very easy to understand. It's very fast to actually do. It's nice as a sanity check to see how difficult is your problem. And it's usually actually pretty good. What is it? Well, the basic idea is if you get at something new, you just try to remember the closest things to it that you've seen before. More specifically, you calculate the distance from your new thing to all the other things you've seen. And then the class of the new thing is the majority class of the closest K things to that. KNN is something called lazy learning. That means there's in vanilla KNN, the simplest form of KNN, there's absolutely no training whatsoever. You get a new data point, you don't do anything to it, and then just when you want to test a new data point and assign a label, then you check the distances. One challenge with KNN is just what to use for K. Values of 1 and 3 are very common. Also, if you have some kind of class imbalance, it's often the case that you'll use weighting. And when you use K equals 1, you can create a diagram called a Voronoi diagram, some type of tessellation of the space. Yeah. So we've got another quiz again. So if you want, pause your video, otherwise we go on. A, what label is the new green point given if K equals 1? We've got 1 point near to it, and that's a purple square. So then the new point would be considered a purple square. If K equals 3, then we've got the majority of the neighbors is a green triangle. So we would consider this point a green triangle. Can KNN deal with this function over here? The answer is yes, sure. KNN can deal with nonlinear functions. This function you might have guessed, maybe probably have guessed, it's an exclusive OR, it's an XOR function. And you can see this cross here would be the Voronoi diagram for that, if these are the samples that you have. Okay, we're about halfway through. So if your stomach is growling, then you might want to take a little break, get something nice to eat, and start again.